My name is Troy Williams, and I am a postdoc at the University of Maryland, College Park, and I'm hosted by Pratap Tokekar and the Ross Lab. Today, I'm going to be talking to you about some research that I did during my PhD and how that has led up into my postdoc research currently. And so for my PhD, I focused on a problem where it's motivated by the fact that robots rely on biased and noisy measurements to perceive the world. However, if we rely on these poorly estimated biases and noises, it can reduce navigational tasks, or at least the performance on navigational tasks, and also reduce safety. So for my PhD, I worked on a project where we developed this concept called state-dependent sensor measurement models. And the overall goal was to improve perception such that we can improve navigational tasks. And so if you could imagine a robot that's navigating in a well-lit environment, the camera that the robot uses to navigate can see very well in that well-lit environment. However, if it's dark, then the robot cannot easily perceive markers that it uses to localize within, for example, a building. And so the distributions that we will get will be relatively different. We're currently working on a project where it stems from what I did during my PhD. And so the project is motivated by the fact that different states affect our measurements differently. That means that different states affect the bias and noise that our sensor measurements produce. And so what we want to do is we want to dynamically determine what states reduce this measurement noise and bias such that we can improve, again, these navigational tasks. And this is motivated by an example where we have an autonomous car that has no access to its external sensors due to damage or for whatever else reason. And so we have to rely on an external observer, such as a drone, to help guide that autonomous vehicle along a path. The problem is that this sensor, for example, a camera, exhibits state-dependent bias and noise. And so we want to determine how we can intelligently place this robot, this drone, such that it observes our car with the minimal amount of bias and noise as possible. And so our technique currently looks at combining constrained optimization with the method that I developed during my PhD, such that we can approach this problem. And so this ends up giving the robotics community a new tool that we can use to dynamically determine where we can place robots such that they reduce perception, noise, and bias, and improve tasks such as navigation.